Spectrometry is the measurement of the interaction between light and matter, and the reactions and measurement of radiation intensity and wavelength. In other words, spectrometry is a method of studying and measuring a specific spectrum, and it is widely used for spectroscopic analysis of sample materials.
A prism spectrometer is an example of a type of spectrometry. It utilizes the distribution of light into its spectral components by means of a prism to measure optical spectrum. The prism refracts light into its different colors or wavelengths. The distribution occurs because the angle of refraction is dependent on the refractive index of the prism's material, which in turn is slightly dependent on the wavelength of light that is traveling through it. Let's take this prism spectrometry calibration experiment as an example.
The prism spectrometers are used to measure optical spectra using the dispersion of light into its spectral components when it passes through a prism. This dispersion results from the fact that the refractive index is dependent on wavelength. It is non-linear, and therefore the prism spectrometer needs to be calibrated in order to measure wavelengths. In order to measure wavelengths, it is necessary to calibrate the system since the angular dispersion is non-linear. In this experiment, the known spectrum of a mercury lamp will be used for calibration purposes, and then measurements will be made for a cadmium lamp.
Inside the spectrometer, the light being investigated passes through slit S or the entry slit to strike the objective O1 or the collimator objective where it gets parallelized. These two components form a collimator and produce a wide parallel beam of light. Due to the nature of the dispersive element, the angle with which light is refracted depends on its wavelength. This leads to a spectrum of thin lines of light, each being observable at a different angle. After refracting at two surfaces of the prism, a parallel beam exits the prism and is focused to an image of the slit in the focal plane of objective O2 or the telescope objective. This then can be viewed via the ocular lens OC or the telescope eyepiece. A lens or telescope is used to form images of the original slit, with images formed using different wavelengths of light at different positions. If a real image is formed, it can be recorded in film or an image sensor, making the device a spectrograph.
In the visible part of the spectrum, the refractive index decreases as the wavelength increases. This can be described by the Cauchy equation in the following form. In principle, it is possible to obtain a mathematical description for a calibration curve from the equation. However, the Hartmann dispersion formula turns out to be better suited to the purpose. Lambda is equal to lambda naught plus C over D minus D naught, where lambda naught, C, and D naught are constant, and D is the particular reading on the plate that gives the distance of the line of wavelength lambda from some arbitrarily assigned 0. For this reason, the experiment, the spectral lines of the mercury lamps are utilized for calibration purposes with the help of Hartmann dispersion equation, and afterwards, the lines of an unknown spectrum will be measured. That's all for today's video.